Welcome to Dungeon Academics. I am Thomas and I will be your instructor. This video, the Reroll Recalculation, is somewhat of a follow-up to the Fighting Stylist and is based on some recreational mathematics I did while stuck on an aeroplane. I was thinking about the formula that was derived in another video to find the average damage of a dice when you re-roll results of 1 and 2. Because of the fighting style, great weapon fighting. A set of additional rules I have been working on for heirloom weapon upgrades gives the option of re-rolling all damage rolls of 1, and if I allowed this to be combined with great weapon fighting, then it would allow re-rolls of 1, 2 and 3. Of course, I wanted to derive a formula to allow me to calculate the mean of these circumstances for any dice. And the next logical step for anyone who enjoys maths for the sake of maths would be to find a general formula for an n-sided die where we re-roll all values up to and including some limit. So that's what I did. There are some things to consider before we dive into the mathematics. We should intuitively know that re-rolling low numbers increases the modified mean, but that re-rolling higher values causes the modified mean to fall. The tipping point is intuitively the mean value of the dice itself. Re-rolling any value lower than the mean will likely increase the final result, whereas re-rolling any values higher than the mean will lower it. Any function we derive should show this result. If the value that we re-roll up to is k, and if k is set to the same as the number of sides of the die, n, then the modified mean must be the same as the mean, as whatever the first roll is, it will be discarded and a new value rolled. Setting the value of k to 0 means that no values are re-rolled, and therefore the mean must also stand unmodified. The formula derived should also show these results. The value of k cannot exceed n, but can be any value from 0 to n itself. Both n and k must be whole numbers and positive, also known as natural numbers, and n cannot be 0, as there is no such thing as a zero-sided die. These are all the expectations and criteria I will be working with, because even if the function returns a numerical value outside these circumstances, they don't reflect possible real-world results. This calculation assumes you must re-roll all values up to and including k, even if it's a bad idea. Re-rolling a 4 on a d6 is likely to return a lower value, though this is not always a bad idea. For example, if you know you need to roll a 5 or 6 to finish a target off, then re-rolling a 4 may be advisable, but in most cases we would use our common sense. Although this formula is derived specifically for Dungeons & Dragons, there are many games where re-rolling some values on a die is possible, so this function is useful across many systems. Let's get started with some algebra and first define some terms we are going to use. N is the number of sides on the dice, and k is the value up to which we are re-rolling inclusively. X bar sub n is the mean roll of a die with n sides. We have looked at how to calculate this in other videos, but the result can be found either using n plus 1 all over 2 or half n plus half. X bar sub n sub k is the mean of a die with n sides when re-rolling values up to and including k. This means that x bar sub 8 sub 3 refers to a d8 where values of 1, 2 and 3 are re-rolled. In the Fighting Stylist, I calculated the modified mean using this template. I started with a general formula for the mean of a dice, then I replaced the values of 1 and 2 with the mean, x bar. This time I can use a more general formula, starting with the regular mean formula, then subtracting all the values up to k, then adding in k times the regular mean. This next step is to split the formula into 3 terms as shown. You should recognize the first component as being the regular mean of the die, so we can replace it with x bar. The second term is the subtraction of the sum of values 1 to k, all divided by n. In the video The Fighting Stylist, I also discuss how to find the sum of an arithmetic sequence, which is what we have in the numerator for this term. Using the rules for arithmetic sequences, I know that the numerator will be k over 2 times 1 plus k. As the whole term is divided by n, we can rewrite it as k times k plus 1 all over 2n, or k squared plus k all over 2n. As this term is a subtraction, it keeps its sign and remains negative. We can also split the two components in the numerator to give minus k squared over 2n and minus k over 2n. Note that both components are negative as the initial fraction was negative. Our third and final term is k times the mean value all over n. I will substitute the mean for its formula, n plus 1 all over 2, which simplifies to k times n plus 1 all over 2. We can multiply out this numerator to get kn plus k all over 2n. Let's split this fraction into its two components, kn over 2n and k over 2n. The first component can be simplified to be just k over 2, while the second remains as k over 2n. Notice that the term k over 2n has the same denominator as our middle terms, which were minus k squared over 2n and minus k over 2n. The two terms with k in the numerator have opposite signs and thus cancel out. This leaves three components, x bar plus k over 2 minus k squared over 2n. How does this compare with the formula derived in the Fighting Stylist? Let's set k as 2 and see how it works out. X bar plus 2 over 2 minus 2 squared over 2n. Simplifying each term, we get x bar plus 1 minus 2 over n, the same as our previous formula. This clears the first check for our new formula. It matches a previously established result. I can choose to replace x bar within the formula for the mean of the dice roll, n plus 1 all over 2. This allows us to combine the first two terms that are fractions over 2, which gives n plus k plus 1 all over 2 minus k squared over 2n. This formula is mathematically pleasing. It uses only the values of n and k and is relatively easy to calculate mentally. The function contains a term with negative k squared in it, and from this we can tell the function will be of the form of an inverted parabola. It will create a hill-shaped curve. This matches our expectations, that the modified mean will go up until k reaches a critical value, specifically just less than the mean of the dice, then will fall again as k approaches n. We can see from the table of results that the maximum value calculated for each die occurs when k is half of n, which is just under the mean of the dice. This matches our expectations. It also shows that when k is 0, or n, the function returns the mean of the dice, which was also a requirement of the function. We can confirm that setting k as either 0 or n always returns a modified mean identical to the regular mean of the die. First we can set k to 0. The first term simplifies to n plus 1 over 2, and the second term has a 0 in the numerator, so it is equal to 0. The regular mean of the die appears out of the modified formula. Setting k to n, we can see that the first term turns into 2n plus 1 over 2, and the second term becomes n squared over 2n, which simplifies to n over 2. Combining these terms, as they have a common denominator, leaves n plus 1 over 2, the regular mean for a die. It would be mathematically prudent to find exactly where the maximum value occurs in a more general way, and to do that we need to find the maximum value of our general formula. The peak of this parabola can be found in many ways, but today I fancy using calculus to find the turning point of the function. Note that we are treating this as a function of k, and so we are treating n as an unknown constant. I'll start with the formula n plus k plus 1 all over 2 minus k squared over 2n. I'll split the initial fraction into its three components as shown, and as two of them no longer have a k in them, they won't contribute any value to the gradient. This leaves us with two terms to consider, k over 2 and minus k squared over 2n. Remember your rules for differentiation. Multiply a term by the power, then reduce the power by 1. K over 2 differentiates to 1 over 2. Minus k squared all over 2n differentiates to minus 2k over 2n, and that simplifies to just k over n. The peak of the inverted parabola occurs when the derivative function equals 0, so let's set the first derivative to 0. Half minus k over n equals 0. That means that half must equal k over n. Multiplying both sides of the equation by n, we end up with half n equals k. The maximum value occurs when k is half the highest score on our dice, exactly our previously intuited value and the value highlighted in the results table. This was supposed to be the end of the video. It was a simple little algebraic exercise that I did for fun, and it produces a neat function that may or may not be useful. But as I was contemplating the topic and preparing the slides for this video, I realized that this whole exercise does carry a vital philosophical issue for all game designers. A few years ago, I was playing an online game of Dungeons and Dragons, and a friend of mine had a character with great weapon fighting. His weapon, through a variety of boons and upgrades, did d10 plus d8 plus d4 damage. When playing around a table, this was easy to use. Roll the 3 damage dice, pick out 1s and 2s, and then roll those dice again. But online this was a different story, as we had yet to figure out macros in the game. His attack button could automatically roll the correct dice for the attack, but then he had to mouse over the damage score to find out if there were any 1s or 2s, and which dice had rolled them. Subtract the total value of any 1s and 2s from the damage, and then use the dice roller to re-roll the specific dice, and finally manually add the new rolls to the total. As you can imagine, this slowed down combat significantly. I learnt an important lesson through that. A rule can be flavourful, balanced and fun, but if it is difficult to implement, then it is a bad rule. Roleplay games tend to be procedurally complex, though this does vary significantly between games. But any additional rules added to a game, or games designed from the ground up, should take care to ensure all their functions are easy to implement. The use of macros in Roll20 turned a rule that was previously frustrating to use into a single click of the mouse. In this spirit, the plethora of bonuses and penalties that somewhat bogged down 4th edition Dungeons & Dragons became the streamlined advantage and disadvantage system of 5th edition. There has to be a balance though. A good rule is powerful and flexible, but also easy to implement. A notion that had me rewrite most of the bonuses in my homebrew ancestral weapon rules. My initial set of upgrades was certainly fun and flavourful, but I realised that many of them would be awkward to use through a virtual tabletop, even with the clever use of macros, or around a tabletop it would require too many supplemental actions and resources to be tracked. A second attempt, with a careful eye to implementation, yielded a better set of upgrades that would frustrate neither the player nor the dungeon master, be they sat around a table or online. This leads me to one of my core principles of game design, what I call Rules Zen. This is easy to talk about in the context of board games as well as roleplay games. Both can be viewed through this lens. A rule set can be measured in 2 key metrics: complexity of gameplay and complexity of implementation. Many games have simple rules and simple gameplay. There are not many moving pieces, and each player has a light load in tracking resources, but there are few gameplay choices and not many viable strategies for players to follow. These games are not necessarily bad though, they are often quick and fun. The opposite end of the spectrum are heavyweight games with complex gameplay and complex rules. Often referred to as Eurogames in the world of board games, they have a lot of resources to manage, but there is a broad and deep range of gameplay styles for players to take. These games are often for more experienced gamers, come in large boxes with hundreds or thousands of pieces, and can take hours to play. There are a few games that have very complex rule sets, but simple gameplay. These tend to be frustrating to a player. A player has a lot to do, but not many choices to make, and playing them can often feel like more of a chore or even a punishment. Lots of work, but not much fun. Finally, we have the best case scenario. Simple rules, but complex gameplay. With few pieces to keep track of and a simple, often elegant rule set, these games offer a rich gaming experience with multiple viable strategies for players to use. I would suggest Settlers of Catan as a great example of a board game in this area. Its rules are not too complicated, and there are many different ways to play and win the game. 5th edition Dungeons & Dragons also just sneaks into this category. Compared to many of its contemporaries, its rules are relatively simple, but the gameplay is still rich and varied. It is my personal opinion that a roleplay game should only have more complex rules than Dungeons & Dragons if it also comes with a significant increase of richness of player agency. I believe that many great games make this move, and some very successfully add a small amount of mechanical complexity in exchange for a richer and subjectively better gameplay experience. As an enjoyer of some quite heavy Euro games, my tolerance for mechanical complexity might be higher than many other players, so I have to be careful that any rules I write must be implementable in a way that will be accessible to other players, though perhaps I may aim at more experienced players rather than many games which are targeted at players new to the world of tabletop role-playing games. A final philosophical note, though one that is more relevant to me as a teacher, is that this whole process is a great example of why we teach algebra. I have had many young students who have had difficulty moving from the concrete mathematics of arithmetic to the more abstract mathematics of algebra. They may view a formula as a question rather than an answer, and they find that any mathematical operation that does not end in a definite numerical answer is, to them, incomplete. They often ask why we learn algebra when it doesn't give a clear answer. When we solve a problem using numerical values, we solve one specific problem. When we create a formula for that problem, we have answered all problems of that type. This table shows all the different values for the mean of many dice, rerolling values from 0 to the maximum value of the dice. There is little value in memorizing all the results of this table, but by knowing the general formula, we are able to calculate all of these values easily whenever we may need to. The formula lets us find all of the values on the table, and more, so it is more powerful than the results themselves. When I started preparing the material for this video, I had no idea of the deeper philosophical thoughts that this topic would stir up. It was just a neat piece of algebra I had enjoyed working on when I was bored. But as I thought more about the topic, the importance of rule implementation and the value of general algebraic solutions naturally came to mind. In many ways, this is the essence of this project. What can understanding the maths behind these games lead us to? And can it make our favourite games, or our next games, better? This concludes our lesson. If there are some game features from any tabletop roleplay games that you would like to know more about the maths for, please ask in the comment section below. And to the dozen or so people who have already subscribed to this fledgling channel, thank you. It means a lot to have people come on this journey with me. And as always, enjoy your next game, whatever it may be.